Welcome students. Welcome students. Welcome students for this live session. Now I am going to explain. The monitor is not coming. Welcome students for this live session. Now I am going to explain JEE model questions regarding the topic electrostatics and current electricity. In electrostatics, you have to divide the chapter into three convenient parts. One is electric charges and also electric field intensity under one part, electric potential and potential energy under second part, capacitor and capacitive circuits under third part. So then only you can answer the correct proper questions regarding to the JEE mains level of standard questions. So if you thoroughly prepare this chapter by splitting like this, then only you can answer the questions properly. So lot of models are to be covered in capacitor problems. Lot of models are to be covered in gas law oriented problems. At the same time, electric field intensity based problems also have to cover. Out of all these questions, first you have to focus more on capacitor oriented problems. Okay, right. First question. In a meter bridge circuit, some extra lengths comes at points A and C, so some more extra lengths should be added at ends for accurate results, which is known as end correction. If end correction at A and B is alpha and beta, then find the value of beta and alpha. If 100 ohm and 200 ohm, then find the value of beta and alpha. If 100 ohm and 200 ohm are used as R and S and balancing length as 33 centimeters. If R and S are interchanged, the balancing length is given as 67 centimeters. So this is the meter bridge circuit. So here this is R, this one is S. The balancing length is supposed to be L. The remaining length is 100 minus L. Practically it is observed that these strips are connected. These copper strips are connected here actually. This is the copper strip is connected to the manganese wire at one end. But by mistake here, this extra length also to be added and taken into consideration. So due to that, here we have to consider the extra length of the manganese wire over the copper strip while connecting this copper strip to the one end of the manganese wire. So due to that, there will be end correction arises, that is called alpha. On right side here also there is one copper strip. So actually here there is a connection in between the edge of the copper strip to the edge of the here copper strip by means of a manganese wire. But practically it will be small, some extra length while soldering of this manganese wire over the copper strip. So here by taking that extra length of that manganese wire in connecting the two copper strips in meter bridge experiment, then in that case end corrections are said to be alpha and beta. So let PQ, instead of PQ I consider R and S are the resistors in left gap and right gap. Balancing length is supposed to be L1 if R and S are in left and right gaps. According to given data here, if R and S are interchanged, the balancing length is supposed to be L2. Then the end corrections are given by the standard formula. It is SL1 minus RL2 by R minus S. In a similar way, beta is equal to, here it is RL1 minus SL2 by R minus S. So here actually we didn't consider this end correction regarding the experiment of here meter bridge, but here some extra length of the manganese wire are to be taken by mistake here in the connection it to the copper strips on both sides. So due to there may be extra resistance you are considering. So due to that extra resistance, that will give end correction in the measurement of balancing length and also here the accurate value of the resistance of the manganese wire. So in that case the end corrections on left side is represented by the equation S into alpha 1 minus R into S into L1 minus R into L2 by R minus S, and end correction on right side is represented as R into L1 minus S into L2 by R minus S. Here in the data, what are the values? R value is given as 100 ohm and S value is given as 200 ohm. So by taking R equal to 100 ohm and S value as 200 ohm and L1 value, what is L1 value here? It is 33 centimeter, and L2 value, by interchanging R and S in the two gaps, the balancing length is 67 centimeter is given in the data. So by substituting all these values of R, S, L1 and L2, we get end correction alpha on left side of the meter bridge instrument is here alpha equal to SL1 minus RL2 by R minus S. By substituting these values, we get alpha value as, here it is 1 centimeter. This is the answer. In a similar way, you substitute all these values in beta equation, you get beta is also 1 centimeter. So here all of you know for meter bridge circuit here, when you know balancing length, when you know resistor values in left gap, right gap, you can find balancing length. But the calculation of end corrections is most important formula in this case. So these are the two formulas you have to kept in mind. These are the two standard formulas you have to kept in mind for calculation of end correction regarding meter bridge experiment. So after calculation, you get alpha and beta value as 1 centimeter and 1 centimeter. For question number 1, answer is A. A equal to 1 centimeter, that is alpha equal to 1 centimeter. Beta is also 1 centimeter. So here lot of mathematical calculation is there in deriving of those two formulas. So for that reason directly I have written the shortcut formulas for end correction of the meter bridge experiment, while by taking manganese wire extrally on meter scale on both sides, but it was not taken exactly as 1 meter. By mistake it was taken some extra length, and also by mistake it was connected in between the two strips, exactly not in between the ends of the two strips on the meter scale. So at that time there will be an error in the measurement of balancing length is obtained. So that error in the measurement of balancing length is called as end correction. So end correction on left side is S into L1 minus R into L2 by R minus S. End correction on right side is R into L1 minus S into L2, where L1, L2 are the balancing lengths when P and Q are in left and right gaps. If they are interchanged, the balancing length is L2. So these are not here it is from left side to balancing point L1, the remaining L2 is 100 minus L1, that is not L2. So L1 is the balancing length when R and S are in left and right gaps. L2 is the balancing length when these two resistors are interchanged. then only the end corrections are given by these two equations as alpha equal to SL1 minus RL2 by R minus S, beta equal to RL1 minus SL2 by R minus S. So, these two are the most important shortcut formulas I have to remember for finding out end correction regarding meter bits experiment. So, lot of mathematical calculations are there in deriving of these two formulas. For that reason, directly I have written the shortcut formulas for this end corrections. Right. Next question. A point charge here it is Q is brought from infinity and is placed at the center of the conducting neutral spherical shell of inner radius A and outer radius B. Then the work done by an external agent. So, work done by an external agent in moving the charge from infinity. See here. So that here it is placed at the center of the neutral spherical shell of inner radius A and outer radius B. So, here work done to move a charge from infinity to the center of the shell, infinity to the surface of the shell or center of the shell is nothing but called as its self energy. So, for any shell here the amount of work done to move a charge from infinity to its center is called its self energy. For shell 1 it is K into Q square by 2A. Let A is the radius. Next, suppose it is surrounded by another one by shell of radius B. Then the amount of work done to move the charge from infinity to the center of the second shell of radius B. Its self energy is U2 equal to K into Q square by it is 2B. Now, what is our question here? Then work done by an external agent. So, work done by an external agent is nothing but the difference of these two self energies of the two shells. So, work done by an external agent is equal to the difference of these two energies, because here A is less than B. Due to that here U1 is more than U2. So, U1 minus U2 is the work done by an external agent in moving the charge Q from infinity to the shell center. So, therefore, W equal to U1 minus U2. In place of U1 I write it as KQ square by 2A minus KQ square by 2B. So, KQ square by 2 into 1 by A minus 1 by B is the equation for work done by an agent to move charge from infinity to the center of the two shells of concentric shells of radii A and B. So, according to given data, answer is here it is KQ square by 2A minus KQ square by 2B is the answer for question number 2. So, it is also another important and standard formula I have to remember. The self energy of the shell is equal to here K into Q square by 2 into radius of the shell. Here radius of the first inner shell is A, outer shell is B. So, therefore, difference of these two self energies of the two shells will give the work done in moving the charge from infinity and to be placed at the center of the conducting neutral spherical shell of inner radius A and outer radius B. So, here what I did here, simply I considered self energies of the two shells of radii A and B are KQ square by 2 into radius of the respective shell. The difference of these two will be the work done by an agent. So, work done by an agent equal to KQ square by 2A minus KQ square by 2B, that will give work done by an agent to move charge from infinity to the center of the neutral shell of inner and outer radius small a and small b. So, this formula is also important standard formula have to remember. Self energy formula on the basis of self energy of the spherical shell. Here this problem is designed. Question number 3. A solid sphere of radius scapular has volume charge density rho equal to rho naught into r square. At a distance x from its center, the electric field at the center of the ring is. So a solid sphere here, this is the solid sphere, has volume charge density rho equal to rho naught into r square, where rho naught is constant, r is the distance from center to the respective point. At a distance x from its center, here it is a solid sphere of volume charge density rho. So that means as we move from center to edge of this one, according to given equation rho equal to rho naught r square, here the density, volume charge density varies in accordance with this distance, radial distance. So due to the charge contained in the sphere from center to edge varies in accordance with the radial distance. So it is a variable amount of charge is contained in the concentric circular disc or rings imagined. So I considered one of the hollow sphere of thickness dr at a distance x, at a distance small r from center of the solid sphere of radius capital R is considered. Then what is the charge enclosed in this solid sphere? Here. So this is the hollow sphere. Within this hollow sphere, what is the amount of charge deposited inside of the solid sphere of radius small r and that layer of thickness dr? That is equal to, here dq is equal to charge per unit volume into volume of this one. What is the volume of the solid sphere it is? So I am going to calculate charge inside of the solid sphere. The outer layer I considered as shell of thickness dr and radius r, but for full inside of this one I am going to calculate charge, that is dq equal to, here rho into volume of this one 4 by 3 pi r cubed into 4 by 3 pi r cubed is the volume. Okay. So but if I take directly, no use. For that reason here we have to written not in this way. Here we have to consider this solid sphere is consists number of shells with increasing radius from center to edge. So due to that, dq is written as rho into volume of this shell is 4 pi r square into dr. So what is rho value? Rho naught into r square into 4 pi r square into dr is equal to dq. So up to this one, charge will be dq, integral of dq equal to integral of rho naught r square into 4 pi r square dr. So from this, charge inside of the solid sphere at a distance small r is equal to q equal to rho naught into 4 pi into, for r square it is r square into r to the power 4 into dr, integral of r to the power 4 into dr within the limits 0 to r. So from this, charge contained in the solid sphere imagined inside of the solid sphere of radius capital R is q equal to 4 pi rho naught into r power 5 by 5. So here charge is directly proportional to, here r to the power 5. Now what we want? Electric field at a distance. From center of the ring, at a distance from center of the ring, O is. So here electric field, what is electric field? Generally q by r cubed into x. For a solid sphere, electric field intensity at a point inside is directly proportional to q by r cubed into x. So E directly proportional to, in place of q I write r to the power 5 by r cubed into, here it is x. But if x equal to r, then only E directly proportional to r power 6 by r cubed. So electric field intensity is directly proportional to x cubed, or electric field intensity is directly proportional to r cubed. See the data here. So what we want here? At a distance x from center only. The electric field from center of the ring is. So here I considered q by r cubed into x. So in place of q, it is replaced by r power 5. In place of r power 5, it is x power 5. So for total R x equal to R, then it is R cube. If it R equal to x, then electric field intensity is directly proportional to x cubed. See the options here. So E directly proportional to x cubed. E directly proportional to x cubed is the answer for question number 3. So E directly proportional to x cubed. So from this I rewrite this equation as E directly proportional to q by, here it is R cubed into x. So q as a function of x, it is x to the power 5 by R cubed. R cubed into, here it is x. So that is x to the power 6 by R cubed. So this R is also taken in as a function of x. Then we get E directly proportional to x to the power 6 by x cubed. Then we get x cubed. So electric field intensity at a point inside of the solid sphere whose volume density varies in accordance with radial distance as rho equal to rho naught into r square is E directly proportional to, here it is x cubed is the answer for question number 3. Next question. The linear charge density on the upper half of the segment of the ring is lambda and at the lower half of the ring is minus lambda. Then the direction of the electric field at the center of the ring is. So here this is the segment of the ring here. For the segment of the ring, upper half is given as positive charge and the lower half is given as negative charge. See what we want here? The direction of the electric field at center of the ring. At this point we want direction of the electric field at the center of the ring here. So I considered one of the elemental strip from the upper half. This elemental strip of angular width d theta is considered. Then electric field intensity due to this elemental strip of charge dq is directed away from this elemental strip at center. So it is dE. So if this dE makes an angle theta with horizontal, the component of the electric field intensity along horizontal axis is dE cos theta. Along vertical direction, downward direction, it is dE sin theta. In a similar way, how to consider identical element at its identical position from lower half having negative linear charge density. So you considered identical element of charge dq having thickness d theta considered at an angle theta from its horizontal position. Then it is a negative charge. So due to that, at point O, electric field intensity is in this direction dE. So when it is theta, here also it is theta. So the component of electric field intensity due to this elemental strip on the distribution of negative charge on the lower half of the ring is dE cos theta towards leftward direction and dE sin theta in vertically downward direction. So this dE cos theta gets cancelled. So net electric field at point O, that is at center of the ring, is in vertically downward direction along OC is represented in the diagram. So net field at point O acts along OC only, acts along the direction OC, that is along vertically downward according to given data along OC. See the options here. So along OC is the answer for question number 4. The linear charge density on upper half of the segment of the ring is lambda. Lower half is also minus lambda. So the direction of the electric field at center of the ring acts along this direction. In this direction, that is the net field. So that is 2 dE sin theta is the net field due to the elemental strip imagined from positive and lower charge negative charge distributions, one over upper, other over the lower surface of the ring according to given data. So electric field intensity acts along here OC direction. So according to given data here, according to options, answer is C for question number 4. Next question. the 2 point charges A and B whose magnitudes are as same as positioned at certain distance from each other with alpha with A at origin. The graph is drawn between electric field string that points between A and B and a distance x from A. E is taken as positive. If it is along the line joining from A to B, from the graph it can be decided that, so 2 point charges A and B are there, suppose here A and B are there, 2 charges, point charges it is, whose magnitudes are same, according to given data Q and Q. Suppose if I consider these two are positive, then plus Q and plus Q. If I consider these two are negative, minus Q and minus Q. So, but I don't know what type of nature of these two charges at points A and B. So, according to given data, but they are separated at certain distance. So, at A, suppose if you imagine one charge plus Q, at B, what is its nature of the charge present at B? So, here charges are placed at A and B having same magnitude is given. Now, when we move from point A to B, electric field intensity due to these two charges varies in accordance with the variation of the distance of these 2 points is given in the following graph. From this, we have to identify here what is the nature of charge present at A and what is the nature of charge present at B. Suppose if these two charges are like charges, we know that there will be a null point to be formed at any one of the point of midpoint or at any one of the point of separation of these two charges. According to given data, both are having same magnitude of charges. For that reason, the null point may be formed at midpoint of their separation. But by keen observation of this graph, so at null point, we know that net electric field intensity is 0. So here from keen observation of this graph, there is no net electric field at any point is 0. For that reason, both charges are not positive. So both are not positive. In a similar way, if both charges are supposed to be negative, in a similar way we will have the null point at midpoint of separation of these two charges, but that is also not observed from the graph. So net field intensity at midpoint of separation of these two charges is also 0. So due to that, here that is also not observed from the graph. So here both are not negative. So here both are positive is wrong, both are negative is also wrong. Now which one is positive, which one is negative? See here, it is A, it is B. Some charge is there Q1, some charge Q2. So at Q1, what is electric field intensity? So it is at Q1, at position origin. Q1 is at origin. So at origin, that is Q1 is at origin, A is at origin. So electric field intensity just nearer to origin, Here electric field intensity due to Q1 is maximum and electric field intensity due to Q2 is minimum. But if I consider one is positive, another is negative, suppose it is positive, it is negative, then electric field intensity at this point will be added up. So due to Q1 it acts away and due to Q2 also along same direction. So here there will be net electric field intensity at this point having some maximum value. As we move from A to B, what happens? Here intensity due to Q1 decreases and intensity due to Q2 slightly increases. So due to that, here this value decreases. And at midpoint of separation, there will be some minimum value of electric field intensity. Then afterwards it slightly increases like this. So as we move from this point to point B, it slightly increases. So this is the variation of net electric field intensity in between A and B. If these two are unlike charges, if A is positive, B is negative, then only there is a possibility of having variation of electric field intensity. First it is maximum, then afterwards it slowly and gradually decreases, becomes minimum at one particular distance, then afterwards it rises. So that is the only possibility of having the variation of electric field intensity in accordance with the radial distance. So answer for this one is here A is positive, B is negative is the correct answer for question number 5. So you have to imagine like that, as the distance between origin to concerned point, what you are going to calculate the electric field intensity, then at that point field due to Q1 and field due to Q2 are to be imagined by you, and both fields are in same direction. So after crossing point B, at this point electric field intensity is towards B due to negative charge, and away from B due to positive charge. So at that point it will be minimum, just minimum. Then afterwards slowly here this value is maximum and this value is minimum. So due to that finally it becomes so slowly it increases. So here in between A and B and just after crossing B also there is a variation of electric field intensity in accordance with the radial distance, as given in the diagram as here like this. So that is only possible if A is positive, that is charge placed at point A is positive and charge placed at B is negative. So Q2 is negative, Q1 is positive is the answer for question number 5. Next, question number 6. A solid metallic sphere has charge 3q, concentric with its sphere is a conducting spherical shell having charge minus q. So a solid metallic sphere has charge plus 3q and it is surrounded by a concentric spherical shell of charge, here it is minus q. Now the radius of the sphere is small a and that of the radius of the spherical shell is small b. Then what is the electric field at a distance small r from the center? Electric field at a distance small r from the center, that we want at point P. Electric field intensity at point P we want. So this point P is inside of the shell of charge minus q, and point P is the outside point for solid sphere of charge 3q. We know that for any conducting shell at any point inside of the conducting shell, electric field intensity is 0. So at this point E due to shell plus E due to sphere, but E due to shell at this point is inside of the shell, so net field, electric field intensity due to shell at point P is 0, and electric field intensity at point P due to solid sphere of charge 3q. So that point is outside point for sphere. So for any outside point here, what is electric field intensity due to solid sphere? 1 by 4 pi epsilon naught q1 q2 by r square. So 1 by 4 pi epsilon naught q1, that is 3q, q2 unit charge to be imagined, by distances it is r square. So answer is 1 by 4 pi epsilon naught 3q by r square is the answer for question number 6. So 1 by 4 pi epsilon naught 3q by r square. C is the answer. Answer is C for question number 6. Simply here we have to consider for shell at any inside point electric field intensity is 0. Now for solid sphere of given charge 3q, that point P is the outside point. For any solid sphere, when charge is given to it, then you have to consider that solid sphere having charge 3q as point charge. So from point charge, the respective point is at a distance r. So what is electric field intensity at a point due to point charge? 1 by 4 pi epsilon naught q by r square. Instead of q, I replace it as 3q. So it is 1 by 4 pi epsilon naught 3q by r square is the answer for question number 6. Next question. For an infinite line of charge density, that is a linear charge density lambda lying along x-axis, the work required in moving charge q from C to A along the arc CA. Here for an infinite line of charge density lambda, along x-axis. So, along x-axis here the line of charge density is lambda is given in the data. So, for linear charge distribution here along the straight line, along line from minus infinity to plus infinity, it is having linear charge density as lambda, that is given in the data. Okay. Now, so this is the linear charge distribution along line with the linear charge density lambda. So, at this point, at a distance, at a perpendicular distance, suppose it is r, electric field intensity due to linear charge distribution of linear charge density lambda is equal to E equal to lambda by 2 pi epsilon naught into r. So, what is the equation for electric field intensity at a point due to line of charge? That is lambda by 2 pi epsilon naught into r is the equation. So, here r is in the denominator, lambda by 2 pi epsilon naught r. Okay, right. So, it acts away, away from line of charge, E equal to lambda by 2 pi epsilon naught r. Now, what is our question? So, in the electric field of this line of charge, one charge q is taken from C to A along the path along arc length CA. So, here C is parallel to the position of B on perpendicular line imagined to this line of charge. So, here when we move from when charge is moved from C to A, this is position B, this distance is A, this is A, this distance is also given as A. Now, so indirectly we are moving charge from C to A in conservative field, nothing but electrostatic field or electric field. So, we know that electric field is conservative field. In conservative field, work done in moving a charge is independent of the path moved by it. It only depends on from which point to which point charge is moved, and it is independent of work done, independent of the path moved by the charged particle in the conservative field. So, what we want here, work required to moving a charge q from C to A, here we want W is equal to here work required to move the charge from B to A. So, as we move from B to A, here electric field intensity varies because E equal to lambda by 2 pi epsilon naught r. R decreases, here electric field intensity increases. So, a charge is moving from B to A indirectly. So, that is taken from C to A along curved path, means indirectly charge is moving from B to A in the conservative electric field. Here electric field intensity increases as charge moves from B to A. So, due to that, work has to be done against electric field force. That work is equal to, that is a variable force here. So, therefore, integral of F into dr. So, that work has to be done against electric field force. Therefore, minus integral of F dr, that equal to integral of F is, what is F here? Q into here it is E, electric field intensity E into dr. So, within the limits here B to this point A. So, that is initial limit is 2A to A. B to A means with respect to this line of charge, it is at a distance 2A. When it is taken from B to A, it is final distance A. Therefore, integral of 2A to A Q into E into dr, that equal to minus Q integral of Q into, in place of E I write lambda by 2 pi epsilon naught r into dr within the limits 2A to A, that equal to minus Q lambda by 2 pi epsilon naught into integral of dr by r within the limits 2A to A. So, from this we get, by reversing the limits of integration, we get Q lambda by 2 pi epsilon naught into what is integral of dr by r? Log r within the limits here, it is 2A to A. So, therefore, work done is equal to Q lambda by 2 pi epsilon naught into log r. In place of r, I substitute upper limit as 2A and lower limit as A, then we get log 2. So work done to move a charge q from C to A in the electric field due to line of charge of linear charge density lambda is q lambda by 2 epsilon naught log 2 here. So by observing all the options here, q lambda by 2 epsilon naught, see here q lambda by 2 epsilon naught, 2 pi epsilon naught or 2 epsilon naught, see here q lambda by 2 pi epsilon naught into log 2, q lambda by 2 pi epsilon naught, this is wrong, here it is also wrong, this one is also wrong. So here you have to correct the option C as q lambda by 2 pi epsilon naught into log base E2. So you correct option C as q lambda by 2 pi epsilon naught into log base E2 is the answer. Here it is typed as 4 pi epsilon naught. So you correct it as 2 pi epsilon naught log base E2. So here in what way I calculated the work done in this case? First we have to observe what type of work it is. This is a work done against variable force. So here we have to use simple integration process within the limits of integration A to A. So after calculation we get C as the answer for question number 7. Okay, you correct that 4 as 2 in question number 7. Next question. Question number 8. 9-point charges are placed on a cube as shown in the figure. The charge q is placed at the body's center, whereas all the other charges are at the vertices. The electrostatic potential energy of the system will be, generally when two charges are separated by a distance, small r, then electrostatic potential energy of the system of these two charges separated by a distance is u equal to minus 1 by 4 pi epsilon naught q1 q2 by r is the potential energy. If n charges are used in the combination, suppose here n charges are used, so to calculate potential energy compulsory one pair of charge is required. So number of pairs is equal to n into n minus 1 by 2. Suppose here for cube we know that there are 8 corners. Suppose 8 identical charges are placed at 8 corners, then the number of pairs have to be imagined is here 8 into 8 minus 1 by 2, that is 28 pairs. So suppose all are having same charge q like this, then this will be 28 pairs are there. This distance is small a, distance between two charges in the side is small a, distance between two charges in the ends of the diagonal is 2a, and distance between the ends of the two charges in the diagonal of the room is root 3a, like that. Here for different distance in between these two charges, here potential energy for pair will be different. At the same time, so indirectly it depends upon the magnitude of the charges and also sign of these charges. Suppose here what is the potential energy? Minus of 1 by 4 pi epsilon naught q1 q2 by r. If one of the charges both are negative, if one is positive another is negative, if both are positive then potential energy will be like this. I consider both are positive, this is the equation. If one is negative then q2 is minus, so minus of minus we get plus. So due to that the potential energy of the system of these charges due to the arrangement of this one at the corners of a cube depends upon here magnitude of the charges, and also depends upon the sign of the charges which are placed at 8 vertices of the cube given as shown below. So out of all these here consideration of options, here we get depends on sign and value of q. So answer is D for question number 8. So if any question is framed, if all are positive charges, then how you calculate the potential energy of the system of 8 charges are placed at 8 corners of the cube of side A, then in that case you have to use the relation. So for 8 charges placed at 8 corners of the cube of side A, then how many number of pairs can be obtained? 28. Out of this 28 here, potential energy between the two charges separated by a distance a, that is 12 pairs, plus potential energy between two charges separated by a distance root 2a, that is 12 pairs, plus potential energy between two charges separated by, here it is root 3a, there are 4 pairs. So like that we can calculate the potential energy of the system of 8 charges placed at 8 corners of the cube of side A. But in this question we don't want that magnitude of the potential energy, only we want what the nature of the potential energy. Will it depends on magnitude of the charges or sign of the charge? That only, up to that point only we confine the discussion. So on the basis of that point, here answer for question number 8 is, so that potential energy, that electrostatic potential energy, the system of these charges having different magnitudes with different signs, here only it will be different. So on that basis we can tick the answer as D for question number 8. Question number 9. A galvanometer gives full scale reading of 50 milliampere when a potential difference across its terminals is 0.15 volt. It can be used as an ammeter of range 0 to 100 ampere by connecting a shunt resistance of. So it is nothing, a problem relates to the conversion of galvanometer into ammeter. So this is a galvanometer. So how you convert galvanometer into ammeter? Simply by shunting, by connecting very low resistance in parallel to galvanometer that acts as an ammeter. So when the current to be measured is supposed to be I. Out of all this current here, only galvanometer can bear some value of current, that is called the maximum current that can be measured by galvanometer, nothing but called as Ig. So it is current for full scale deflection in the galvanometer is Ig. It is not only the current through galvanometer, you have to understand this Ig value as the current required for maximum or full scale deflection in the galvanometer. Now the remaining amount of current is deviated through shunt, I minus Ig through shunt. Now here, what is the shunt required? What is the shunt required to measure current of I when galvanometer bears the maximum value of current of Ig is S is equal to G by I by Ig minus 1. So this is the basic equation. Now according to given data, the current flows through galvanometer is given as, here it is 50 milliamperes, and the voltage across the terminals of the galvanometer is given as, what is the voltage? Here it is 0.15 volt. So from this the resistance of the galvanometer can be calculated as, here R equal to V equal to IR, R equal to V by I, V by I, Ig. V value is 0.15 by Ig value 50 milliampere. So from this we can calculate G value, ohm. Now you substitute this G value in this equation. G value by I value is to measure, to convert this one into ammeter of range 100 ampere, 0 to 100 ampere. Then I value is 100 by Ig value 50 milliampere, 50 into 10 power minus 3 minus 1. So you substitute G value in this equation and substitute I value as 100 ohm, 100 ampere, and Ig value as 50 into 10 power minus 3. Then after calculation you get shunt resistance as 0.00075. Will check that answer. The shunt resistance as 0.0015. So answer is C. That is 0.0015. 0.0015 ohm is the shunt resistance. So simple question it is, but you have to consider Ig value is the current for full scale deflection in the galvanometer. It is not the current flows through galvanometer. For full scale deflection the required current is Ig. Okay, right. Next, question number 10. An electrostatic field in a region is radially outward with magnitude E equal to, in electrostatic field, the radial, in radial direction electric field intensity is represented as E equal to alpha into R, where alpha is constant, that is the radial distance. Now, the charge contained in the sphere of the radius R in this region, charge contained in the sphere, here like this. In this sphere, what is the charge contained? So by considering a sphere of radius R, this distance as R, and the center of that sphere is at this origin or center of this field, then what will be the charge contained in this one. So here we got to consider charge. What is charge here? So here charge is equal, electric field intensity is given. So electric field intensity is given, charge is equal to dq equal to, here it is, E into, what is E value? E equal to 1 by 4 pi epsilon naught into q by r square is the equation for if q is the point charge. But charge can be written as dq equal to E into, so for this conservative field here, as area increases from center to radially outward direction, then the charge in the elemental strip in that area is represented as E into dA. So total charge can be obtained as integral of dq equal to integral of E into dA. For this one, area is E into integral of E into dA is, it is 4 pi r square, but E is constant, that is E equal to alpha into r into 4 pi r square. So therefore it is q equal to 4 pi alpha into r cubed. 4 pi alpha into r cubed is the basic equation for charge here. So what we want here, at small r it is, at small r it is, so what is E value? E into dA 4 pi r square. E is S alpha into r, the charge is equal to, sorry, this one is the flux. So this one, this one is the flux passing through the area but not charge. So therefore d pi equal to E into dA. In place of flux here it is, we know that dq by epsilon naught equal to E into dA. Therefore dq is equal to epsilon naught into E into dA. Therefore integral of dq equal to, that equal to q equal to epsilon naught into, here it is E value is, what is E value? Alpha into r into dA is 4 pi r square. So but up to what point here? The sphere of radius small r equal to capital R. So from this it is 4 pi epsilon naught alpha into r square into r cube. So at a distance small r equal to capital R, then it is r cube. So answer is 4 pi epsilon naught alpha into r cube. So here I considered the solid sphere. See here, solid sphere of radius capital R by considering the center of the sphere at the center of the field which acts radially outwards in according to the equation at which electric field intensity varies radially as E equal to alpha R. So from this equation I calculated flux passing through the area in the form of a sphere in that region of electric field intensity. The flux passing through that region is d pi is equal to E into dA. In place of d pi I written as E into dA, that in place of dA I have written as 4 pi r square. In place of A it is alpha naught in alpha into r equal to the charge contained in that zone by epsilon naught. So here the charge q equal to epsilon naught alpha into r into 4 pi r square, that will give 4 pi epsilon naught alpha into r cubed, that will give the total charge present inside of the solid sphere imagined in the region of electric field intensity E equal to alpha r. Right, next question. By which of the following single load resistor the load bridge should be replaced so that power to the load remains unchanged? Power to the load remains unchanged. So simply here power to the load remains unchanged means So what is the R value is given? R equal to 3. See the sentence once again. The load bridge is to be replaced so that power to the load remains unchanged. Power to the load remains unchanged means whatever the resistance of this bridge, that will be equal to the resistance of the, that is internal resistance of the cell used in the supply. So here in this case the internal resistance is R, that is also equal to the individual resistor values in the load bridge. So here I am going to calculate the effective resistance of the load bridge in between these 2 points. Okay. So here first, see here from this, these are the points according to given data. This is the cell. This is smaller, all the values are smaller. Are connected in the circuit in between these 2 points. So I am going to calculate effective resistance between A and B. So for this, for our convenience of calculation, now I am going to use nodal method here, that is zero potential method here. So I fix a battery of 100 volt for our convenience. I don't know this potential. I fix a battery of 100 volt for our convenience, 100 volt. And you have to assume in between these 2 connecting terminals at one of the point as zero potential. I considered B as zero potential. Then what is the remaining potential at the other end, other connection? It is, I am sure, 100 volts plus 100 volts. Now you have to identify the junctions. What is a junction here? It is a point where more than 2 resistors are connected. So this is one of the junction, this is another junction, this is another junction. So how many junctions are there? 1, 2, 3 along with A and B. A and B I represent potentials as 100 volt and 0 volt. So now here along the path here, along this path here, along the path ACB, along the path ACB here the voltage drop at point C is 50 volt, because along the path, forget about the remaining circuit, along the path ACB the voltage drop at point C is, it is 100 volt, it is 0 volt, so compulsory it must be 50 volt is the voltage at point C. Now along the path ADE, along the path ADE, here there are 2 junctions are there. Let voltage drop at this junction D is X. Then along the path from A to E the drop is 100 volts. At D let potential drop is X, then the potential drop at E is 100 minus X. So here I fix one battery of potential 100 volt for our conveniency of calculation by considering potential at B as 0 volt and potential at A as 100 volt. Now what? At C here it is also a junction, node indirectly, junction. So along the path ACB, forget about remaining connections, along the path ACB here there are 2 equal resistors are there. So here 2 equal resistors are there. So here same amount of voltage is dropped. So if 50 volt, here 50 volt is dropped. So potential at C is 50 volt. Okay. Next, along the path ADE there are 3 resistors are there, R, R and R. But these 2 resistors are connected in series along this path. So let potential drop at point D is X. Then what will be the potential drop at point E? 100 minus X. So there are 1, 2, 3 nodes are there, 3 junctions are there. How many unknown terminals are values are there here? X, only one X unknown term. So at node, at any junction at node, the algebraic sum of current meet at a junction is 0. Algebraic sum of currents meet at a junction is 0. That is sigma of delta V by R is equal to 0. I consider junction D. At junction D, what are the currents flow here? Like this. At junction D, there are 4 connections are there. D to A, D to C, D to E, and D to E in the other path. So there are 4 connections are there at junction E. So current is potential drop by resistance. So along the path D to A, at junction D along the path D to A, what is the current here? X minus 100 by resistance is R, plus along the path D to C, it is X minus 50 by R, plus along the path D to E, X minus 100 minus X by R, plus along the path DE, D to E along this path, that is X minus of 100 minus X by the resistance is 2R, that is equal to 0. The algebraic sum of currents meet at a junction D is 0. Current through path DA is X minus 100 by R. Current through path DC is X minus 50 by R. Current through path DE is X minus 100 minus X by R. Current through this path here, this path DE is X minus of 100 minus X by 2R. So here X minus 100 by R plus X minus 50 by R plus X minus of 100 minus X by R plus X minus of 100 minus X by 2R. So after calculation, we get here X value is equal to, X value, do the calculation. After calculation, we get X value is 60 volt. X value is 60 volt. Now what we want? The resistance we want, the total resistance between A and B we want. So when we know X value, then see here, what is the effective resistance? R effective. Voltage applied is equal to total current drawn from the source into R effective. So R effective can be written as voltage applied by total current. So here in this circuit there will be I1 current, here it is I2 current. Whatever the current division through different resistors in this complicated circuit, here finally the current may be either this branch current plus this branch current, that will equal to I. Whatever the current drawn from the source, that will be equal to current through these last 2 branches, they merges into I. So therefore it is I1 plus I2. Applied voltage applied is 100 by, what is I1? Here I calculate it as 50 volt. I calculate here it as 60 volt. So what here at this point here 100 minus 60, that is 40 volt. So with the help of nodal method, I calculated X value as 60. Then here at this point 50 volt, at this point 60 volt, here voltage is 40. Now here the current is from C to B, current from E to B, that merges as I. Current from C to B and E to B, that merges as I current, these 2 currents. So what is current through C to B? 50 minus 0 by resistance R. Current from E to B, 40 minus 0 by resistance R. So therefore here it is 50 minus 0 by resistance R plus 40 minus 0 by resistance R. Therefore it is 100 by 90 into R, that equal to 1.1 R. But what we want? R effective. So what small r value is given as R equal to 3 ohm is given. So R effective of the load bridge circuit is equal to 1.1 into R, that is 1.1 into R value is 3, that is 3.3 ohm is the resistance, the single load resistance, the equivalent resistance value of the single load resistance is 3.3 ohm is the answer for question number 11. So I solved this question by using nodal analysis method, nodal method or zero potential method. So what I did here, I consider the circuit and connected a battery of known potential 100 volt between A and B, and I considered potential at B as 0 volt and potential at A as 100 volt, and at C here along the path ACB, here there are two resistors at point C. Out of 100 volts drop, there will be 50 volt drop potential. Along the path ADE, here there are R and R3 resistors are there. So I don't know in what way that potential difference will be shared. So I considered at junction D unknown potential as X. Then at point A it is 100 volt. At the other end point of the junction, the remaining potential drop is 100 minus X. Now only one unknown term is there, that is X, according to our convenience of calculation. In some other problems, there may be you have to identify X, Y and Z also, in some, depending upon the number of junctions, depending upon the required values. So now by using nodal analysis here, indirectly by using at each and every node, the algebraic sum of currents meet at a node is 0. So that is potential difference by resistance between the two junctions is 0. So at this junction I considered. So at junction D, so there are 4 connections, D to A, D to C, D to E and D to E along this 2R resistor. Simply I calculated current as potential difference by resistance along 4 paths equated to 0. So after calculation I got X equal to 60 volt. So potential at D as 60 volt, potential at E as 40 volt I calculated. Now here when it is 60, it is 50, it is 40. Now what we want? Effective resistance. Effective resistance is voltage applied across. Voltage applied across the load bridge is 100 volt by the current flows through the circuit by means of the source. That is, we don't know in what way this current division takes place. So I consider finally how many branches are there? Lastly 2 branches. Whatever may be the current division takes place, the current comes from the 2 branches, last 2 branches, the sum will be equal to I, what is the total current. So here for last branch here it is 50 minus 0 by R is the current. Here it is 40 minus 0 by R is the second current. Meeting of these two will be I. So therefore 50 by R plus 40 by R. The 100 by 90 by R is taken to numerator. From this we get 1.1 R. So after calculation here small r value is given as 3 ohm. Then after calculation the effective resistance of this load bridge is 3.3 ohm is the answer for question number 11. Most important and standard model question. I explained this question in a different model way, with a different methodology, that is called as nodal analysis. Right. Next question. Consider a system of n concentric conducting shells of radii R, 2R, 4R, 8R and 2 to the power n minus 1 into R respectively. If inner shell is earthened and Q charge is given to the outermost shell, the charge appears on the innermost shell. So if number of shells are arranged like this, this is the radius of the innermost shell, this is the radius of the outermost shell. If charge is given to the outermost shell as Q, then the charge on innermost shell is equal to minus of charge given to the outermost shell into radius of the innermost shell by radius of the outermost shell. So what is the equation for charge on innermost shell of radius R inner? That is, charge given to the outer shell is Q, that is minus of Q into radius of the innermost shell by radius of the outermost shell. See the questions here. Radius of the outermost shell is, this radius is given as 2 to the power n minus 1 into R. Therefore charge on innermost shell is equal to minus Q into what is the radius of the innermost shell, small r, divided by 2 to the power n minus 1 into R. This R gets cancelled, that is minus Q by 2 to the power n minus 1 is the charge present on innermost shell when it is earthened. When it is earthened, it is. When charge Q is given to outermost shell, then charge present on innermost shell is minus Q into R by 2 to the power n minus 1 into R. R gets cancelled, minus Q by 2 to the power n minus 1. So for question number 12, answer is minus q by 2 to the power n minus 1 is the answer for question number 12. It is also another shortcut formula for calculation of charge present on inner shell when charge given on outer shell and corresponding radii are given in the data. So this is the equation for calculation of or finding of charge present on innermost shell and also that innermost shell to be earthened. Then only all these equations are applicable. Okay, right. Question number 13. In the network shown, the points A, B and C are at potentials 70 volt and 0 and 10 volt respectively. Then what we have to identify? Potential at junction D, the currents in the sections AD, DB and DC, current in the sections AD, right? So current in the sections AD, DB and DC, and also potential junctions that we have to identify. So this is the given circuit. So outright this is 0 volt, here it is 10 volt, this one is given as 70 volt, this is D, this is let V volt is the voltage and it is 10 ohm resistance, here it is 20 ohm, 30 ohm. So what we have to calculate? Potential at junction D and also current flows through AD and BC, it is B, it is C, it is A. So let I be the current flows from A to D and at junction D it splits as I1 through DB and splits as I2 through DC. Now we apply Kirchhoff's law. So from this point here, what is I1 here from this branch A to D? A to D, here it is 70 minus V. 70 minus V is equal to I into resistance 10 ohm, 10I. From D to B, what is the current flows here? I1 is the current flow. Potential drop is V to 0 volt. V minus 0 equal to 20 into I1. And from D to C, what is the potential at D? V, at C 10 volt. So V minus 10 is equal to 30 into, here it is I2 can be written as, at this junction I splits as, here I1 and I2 and I2 can be written as I minus I1, that is 30 into I minus I1. So now you substitute the second equation in first one, second equation third one. So from this 70 minus V has 20 I1 is equal to 10I, equation 1. And V has 20 I1 in third equation, we get 20 I1 minus 10 is equal to 30 into I minus I1, equation 2. How many unknown terms are there? I and I1. How many equations are there? 2 equations are there. So from this easily we can calculate I1 and I2. We can calculate I1 and I2. So after substitution, after I1 and I. So after calculation of I1 and I, then what we want? V value. Simply you take V equal to 20 into I1. After calculation you get I1 value as 2 ampere. Therefore 20 into I1 is 2, that equal to 40 volt is the potential at junction. 40 volt is the potential at junction D, that is 40 volt. So do the calculation. After calculation you get I1 as 2 ampere. So on that basis you calculate I. So here from this current, the potential at point D is 40 volt is correct. The currents in the section AD, DB and DC are also in the ratio 3:2:1. 3:2:1. That is also correct. So A and B are correct answers. Answer is A. Okay, A, B is the correct answer. Both statements are correct. Okay, so do the calculation. After calculation you get the I1 value as 2 ampere and potential D value as 40 volt. When you know I1, you substitute I1 value in any one of the equation, you get I value. So when you know I value, you can identify current through AD, current through DC, DB and DC. So those are in the ratio 3:2:1, and potential at junction D is 40 volt. Right. Question number 14. In a certain region of space, the electric potential is given as V equal to, it is AXY minus BX square plus CY. Now what we want? At which points is the electric field is 0? When potential in a region of electric field intensity is given, then the electric field intensity in that region is obtained as E equal to minus dV by dr, that equal to minus of dou V by dou x into I cap, that is E bar, plus dou V by dou y into j cap, plus dou V by dou z into k cap. This is the equation for electric field intensity vector in terms of variation of potential at a point in a space in accordance with position coordinates x, y and z. Okay, see what is the equation for V? AXY minus BX square plus CY. While doing partial differentiation of this equation with respect to x, you have to consider all the remaining y and z components are same. While doing the partial differentiation with respect to y, x and z are same. But here there is no z term, need to do differentiation with respect to z, that is 0. Okay, therefore here it is Ex is equal to minus of dou V by dou x, that equal to minus of, now what is dou AXY minus BX square plus CY, minus BX square plus CY. So by differentiating this one, dou by dou x, according to given data, the net electric field intensity is 0. See here, electric field is equal to 0. So due to that, this is also equal to 0. Therefore A into x, you are doing partial differentiation with respect to x, so y is also constant, into for x1 minus b into for x square, it is 2x, plus c and y are constant 0, that equal to 0. So from this ay equal to 2bx. In a similar way, ey is equal to, by doing the same differentiation of the same equation with respect to y, so then it is minus of, so ey equal to, it is minus of is there, so minus of a into x into for y, it is 1 minus bx square constant 0 plus cy c equal to 0. Therefore ax is equal to minus c. So x is equal to minus c by a. You substitute x equal to minus c by a, 2 in 1. Then y equal to 2b by a into x is minus c by a, that equal to minus 2bc by a square. Minus 2bc by a square is the equation for y. See the data? Yes, y equal to minus 2bc by a square, x equal to minus c by a. So for question number 14, answer is A. So what I did here? I did partial differentiation of the given potential function with respect to x and y, but there is no z term, so Ez is 0. So it can be valid for any value of j. So answer is, so for any value of j and for y value and for x value I calculated. So here at this point net electric field intensity is 0. So simple calculation it is. Right. Question number 15. A parallel plate capacitor is charged to a potential of 50 volt. It is discharged through a resistance. After 1 second, the potential difference between plates becomes 0. So for parallel plate capacitor of capacitance C and charged to potential 50 volt. When it is discharged through resistance, then after some seconds the potential drop across this one, V equal to, all of you know, V naught into e to the power minus t by RC is the basic equation for the potential across resistance after t seconds when it is discharged from capacitor. So V equal to V naught into e to the power minus t by RC, that value is given as 40. equal to 50, peak value is 50, 50, 50 into e to the power minus t by RC. Therefore, 40 by 50 is equal to e to the power minus t by RC. That is 4 by 5. Now, what we want? See the options here. The potential difference between the plates after 2 seconds will be 32 volts. So, what is the potential difference? Potential difference between the plates of the capacitor after 2 seconds, that is V naught into e to the power minus 2 by RC. That is V naught is 50 into e to the power minus 1 by RC whole square. It is t equal to 1, it is. T is given as 1. Second case, t is given as 2. So, 50 into e to the power minus 1 by RC is 4 by 5. 4 by 5 whole square. That is 16 by 25 into 50, we get 32 volts. So, what is the potential? Potential difference between the plates of the capacitor after 2 seconds is 32 volts. So, second option is correct. Simply have to check the options. Okay. So, answer is 32 volts for second option B. In a similar way, I will check the first option. The fraction of stored energy after 1 second. So, what is the energy stored here? U1 by U2 is equal to half C V1 square by half C V2 square. After 1 second, what is the potential here? V1 40 by initially the energy is 50. Initially the potential is 40. After 1 second, it's initially the potential is 50 volt. After 1 second, the potential is 40. So, it is square. So, from this it is 4 square, 16 by. So, the fraction of stored energy after 1 second is 16 by 25 is also the answer for this question. So, for question number 15, answers are A and B. Answers are A and B. Both are correct. Okay. So, this is wrong. This one is also wrong. So, A and B are correct answers for question number 15. Next question. Question number 16. The charge on the capacitor of capacitance 10 microfarad connected as shown in the figure at steady state. So, we know that at steady state here, capacitor doesn't allow DC. So, here there is no current flows through, 3 ohm resistor. So, only the circuit is a battery connected to 2 ohm resistor along in connection with a capacitor. So, whatever the voltage drop across 2 ohm resistor, that will be equal to voltage drop across capacitor. So, what is the voltage drop across 2 ohm resistance when capacitor is at steady state? That is here 2 volt. So, that is 2 volt is the voltage drop across capacitor at a steady state. At that time, what we want here? Then charge on the capacitor. So charge on the capacitor equal to Q equal to CV. What is the capacitance value here? 10 microfarad into the potential drop across capacitance when capacitor is in steady state is whatever the voltage drop across resistance, that is the voltage drop across capacitor, into 2, that equal to 20 microcoulomb. 20 microcoulomb is the charge on the capacitor of capacitance 10 microfarad when it is connected to a battery and resistor as shown in the figure. So for question number 16, answer is 20 microcoulomb is the answer for question number 16. Next question. Two bodies A and B, each of mass small m and carrying charge q, are rotating with constant speed v in the circle of radius r by 2 on the smooth horizontal surface and are connected by a spring constant k. The total energy of the system is. So two bodies A and B, each are having mass m and having charge q, are moving on a circular path of radius r by 2 by means of connecting with a spring of force constant k. Next, total energy of the system. So what is the total energy of the system? Let it moves with speed v. Here also it moves with same speed v because both are having same mass and same charge. Both are at same distance from center of rotation. Now what we want? Total energy of the system. So total energy of the system is equal to kinetic energy of the first particle plus kinetic energy of the second particle plus these two particles are having some charge, due to that there will be electrostatic potential energy between one and two particles, plus at the same time there will be a spring force exists between these two charges at equilibrium. Here the spring force will be here kx. So therefore due to that the energy stored in the spring is half kx square. So this is the total energy of the system. So our kinetic energy of the, that is translational kinetic energy of the first one is half mv square, and for second one is also half mv square, plus potential energy of the system of these two particles of charges q1 and q2 separated by a distance r, that is k into q1 q2 by r plus half k into natural length of the spring is supposed to be L0. Then the distance between the extension of the spring is, that is, what is the distance here? Distance between the two ends of the spring is r. So extension in the spring is equal to r minus L0. R minus L0 is the extension in the spring. So half k into r minus L0 whole square. So it is the total energy of the system of these two particles are moving on the circular path with linear velocities v and v separated by a distance small r. So according to given data, here answer is no option is matching with that result. So answer is D, none of the above. None of the above is the answer for question number 17. Correct answer is half mv square plus half mv square. Mv square plus k is 1 by 4 pi epsilon naught into q square by r plus half into k into r minus L naught whole square, where L naught is the natural length of the spring. L naught is the natural length of the spring. So at the equilibrium they are rotating in the circular track of radius r by 2. So r by 2 plus r by 2, r is the distance between these two particles at equilibrium. So note that here initially this equilibrium distance is more than the natural spring length as L naught. So this is the final equation for total energy of the system of these two particles under rotation. So answer is none of the above for this question. Question number 18. N resistances, each of resistance capital R are joined with capacitors of capacitance C, and the battery of EMF capital E, battery of EMF E as shown in the figure. In steady state condition, the ratio of the charges stored in the first and last capacitor is. See the connection of all these capacitors along with the resistances connected to a battery are in parallel to each other. So, how many number of resistors or how many number of capacitors are connected in parallel to a battery of EMF E, then all are said to be here in parallel. Then the voltage drop across first capacitor is equal to voltage drop across first capacitor is equal to voltage drop across last capacitor also. So, what we want here? The ratio of the charges, capacity values are same. So, Q1 by Q2 is equal to CV1 by CVN, last one. CC gets cancelled, all are having same capacitance. The V1 equal to Vn, therefore it is answer is V1 equal to Vn, CC is same. So, answer is 1:1 is the answer for question number 18. So, problem seems to be difficult, but it is very easy. So, to confuse the students, sometimes this type of questions may arise in the final paper also. Okay, right. Next question. Electric current flows. Electric current flows along an insulated strip PQ of the metal conductor. The current density in the strip varies as shown in the figure, that is in the graph as shown below. Which one of the following statements could explain this variation? So, current density and distance along the strip from P to Q is given in the data. The nature of the graph is given, that is a straight line having negative slope is given. So, this is a strip from P to Q, in a strip that is P to Q. What is given here? The current flows to the along the insulated strip PQ of metallic conductor. Current flows like this. See the options here. The strip is narrow at point P than Q. Strip is narrow at point Q than P. The potential gradient along the strip is uniform. The resistance per unit length of the strip is uniform. So, these are the options are given. So, we have to think in the dimension. Okay, strip is narrower at point P than Q. Strip is narrower at point Q than P. So, indirectly you have to imagine this strip is not uniform, but one of the option is also given. That option is not given in the data. So, we have to consider compulsory the strip is a non-uniform strip. So, area of cross section at P is not equal to area of cross section at Q according to given 4 options. We have to assume like that. So, in this case the current flows through this one is equal to I. So, what is the resistance of the strip here? Resistance of the strip equal to rho L by A. So, this resistance R is inversely proportional to A. R is inversely proportional to A. I multiplied this one with the current flows through the strip is I into R is inversely proportional to I by A. But I into R is the potential difference between the ends of the strip. So, V directly proportional to I by A is J. Between the ends PQ, resistance of the strip is rho L by A. So, R is inversely proportional to area of cross section of the strip. I multiplied with IR on both sides. IR is directly proportional to I by A, but IR is the potential difference between these 2 points P and Q in the strip, is directly proportional to current density. So, according to given data here, see here, current density decreases along with the distance. Current density decreases along with the distance R. So, current density decreases means potential difference also decreases. Potential difference also decreases. When potential difference also decreases, due to that current density also decreases. So, what is current density? J equal to I by A. When current density decreases, the area of cross section increases. As we move from P to Q, here the current density decreases. So, here area of cross section increases as we move from P to Q. So, for this strip here, this is point P, this is point Q. So, here current density decreases by increasing area of cross section. So, area of P is less than area of cross section at Q. So, on that basis you have to take the answer. For question number 19, answer is strip is narrower at P than at Q. Strip is narrower at P than at Q. So, option A is correct for question number 19. B is wrong. the potential gradient along the strip is uniform. No, potential difference decreases by increasing the length. So potential difference decreases by increasing the radius, by increasing the distance, radial distance, not resistance here. This is resistance here. This R is resistance here. Okay, here R is rate distance here. In the graph, this R is distance. In the equation I have taken it is resistance. Okay, so what is potential? Potential difference decreases as radial distance increases. This distance. So it is not uniform. Next, the resistance per unit length of the strip is uniform. So here resistance is, the R is inversely proportional to area. So it is not uniform. It is not uniform. So out of all these options, option A is correct. Question number 20. A metallic rod is placed in the uniform electric field. Select the correct options. Inside the rod there will be an individual electric field from B to A. Free electrons will accumulate at the end of B. Potential at end A will be more than that of B. Like that, options are given. So this is the electric field intensity E naught. A rod is kept. A rod is kept inside of the electric field intensity. So due to that, here the negative charge is induced and positive charge are induced at the front end and at the back end of the rod, where positive charge is induced at right end of the rod kept in the electric field directed from left to right, and negative charge is induced at this end. So according to given data, it is end A. At end A, negative charge is induced, at end B, positive charge induced. So inside of the rod there will be an electric field is induced. So net electric field in between the ends of the rod is, net electric field is equal to E naught minus induced electric field. So suppose at this point if you want to find the electric field intensity, it is due to the consideration of this external electric field and also due to the induced electric field developed inside of the rod. So at any point outside of the rod, here you have to consider electric field not only due to electric field developed inside of the rod, but also due to electric field outside of the rod. So it is due to both fields, field due to outside field, external field, and field induced inside of the rod also to be taken into consideration for calculation of net electric field at this point. And electrons are accumulated at end A, and positive charge is accumulated at end B of the rod. So potential at B is more than potential at A. Potential at B is more than, because always positive end will have more potential than that of negative end. So potential at end B is more than potential at end A. Right. Next. So answers: inside of the rod there will be an induced electric field. Yes, right, correct. The free electrons will accumulate at end B. No, free electrons will accumulate at end A. It is wrong. Now potential of the end A will be more than that of B. No, it is less than that of B. It is also wrong. Next, electric field outside of the rod will not change due to induced charged field in the rod. No, it will change. It will change due to induced electric field in the rod. So out of all these, option A is correct. Question number 21. A hollow conducting sphere of inner radius R and outer radius 2R is given a charge Q as shown in the figure. Then potential at different points. This is given as charge Q. Okay, the radius are Kepler and 2R are the radius of the inner shell and outer shell. Now what are the points? A, B, C. This is A, this is B, it is C. A, B, C. So point A, B are inside of the outer shell. Point A, B and C. A, B and C are inside points. Inside points of outer shell. So due to that, at all points inside of the shell having some charge Q, potential is same at all points, that is equal to potential at surface. So potential at A equal to potential B equal to potential C equal to 1 by 4 pi epsilon naught Q by 2R whole square. So what is the equation for potential at A? Are equal to B equal to C, that equal to 1 by 4 pi epsilon naught charge given to outer shell is Q by it is 2R whole square. That is potential at A are equal to B or equal to C. Now what is potential due to? Potential due to this inner shell. So no charge is given. So only charge is given to outer shell. Charge is given to only outer shell. Due to that, all these points comes under the effect of charge given to outer shell, but not due to the inner shell, because there is no charge on inner shell. For that reason, all these points A, B, C are considered as inside points of shell of charge 2R, shell of charge Q and radius 2R. We know that for any shell having charge Q, at all inside points potential is same and is equal to potential at surface. That equal to potential at surface. Therefore, that equal to 1 by 4 pi epsilon naught into Q by 2R whole square is the answer. So out of this, here potential at A, B, C and O is same. Potential at A, B, C and O are same. So the answer for question number 21 is D. Question number 22. As shown, the circuit is made of 8 different resistors. It is found that R1 equal to 4 ohm. The resistance between A and B is 2 ohm. Now replace R1 by 6 ohm resistor. Then what is the resistance between A and B? You consider this one as R1. For remaining circuit I considered for remaining circuit whose resistance is supposed to be X. So here X is connected in parallel to R1, then X into R1 by X plus R1, that value is given as 2 ohm. So X into R1 value is 4 by X plus 4 is equal to 2. Next, R1 is replaced by 6 ohm, then what is the resistance between A and B? If R1 is replaced by 6 into X by 6 plus X is equal to, here it is X dash, that we want. So from this equation, by multiplying this one, 4X is equal to 2X plus 8, 2X equal to 8, X equal to 4 ohm. So from the first sentence of the given data, here I calculated the resistance of the remaining circuit except R1 is 4 ohm. Okay, resistance of the remaining circuit except R1, that is 4 ohm connected in parallel to R1, that will give the effective value of resistance as 2 ohm. If R1 is replaced by 6 ohm, then resistance is to be calculated. So 6 into 4 by 6 plus 4 is equal to X dash. So from this X dash is equal to 24 by 10, that is 2.4 ohm is the value of X dash. The value of X dash, that is effective value of resistance in between A and B if R1 is replaced by 6 ohm. So answer is 2.4 ohm is the answer for question number 22. So what I did here, so except R1, for remaining resistors, the effective resistance I considered as X. So R1 parallel to X and its effective value is given as 2 ohm. From that I calculated the resistance of the remaining resistors except R1 as 4 ohm. Now if R1 is replaced by 6 ohm, 6 parallel to this 4 ohm, effective resistance is 6 into 4 by 6 plus 4, that is 2.4 ohm is the answer for question number 22. Question number 23. A parallel plate capacitor with a dielectric slab completely occupying the space between plates is charged by a battery and then disconnected. The slab is pulled out with constant speed. Which of the following curves represents qualitatively the variation of the capacitance of the system with time? So here capacitance, this is the capacitance, and having the plate of thickness, plate of width B and length is small l, and distance of separation between the plates is d. Then the capacitor at which air is the medium between the plates is C naught is equal to epsilon naught A by D, that is equal to epsilon naught A is L into B by D. Now, according to given data, in between the plates of capacitor, a dielectric is completely and fully occupied. Now, when it is slowly pulled out, with constant speed, then after t seconds, this is the position of the dielectric in between the plates of the capacitor. So, let it covers a displacement x. Then the length of the dielectric in between the plates of capacitor is L minus x. The width of the plate is B. Now, at that time, there are two capacitors are formed. One is air capacitor, another one is dielectric filled capacitor. For air filled capacitor, the length is x. For dielectric filled capacitor, length is L minus x. So, these two are connected in parallel. Air filled capacitor and dielectric filled capacitors are connected in parallel. For air filled capacitor, capacitance is C1. For dielectric filled capacitor, capacitance is C2. So, therefore, effective capacitance is both are connected in parallel. So, C1 plus C2. What is C1? Epsilon naught into, for air filled, it is length into breadth, x into B by distance is D, plus for second capacitor is filled with the dielectric. So, K into epsilon naught into K into epsilon naught into length is B, length is L minus x, breadth is B by D. So, C effective is equal to epsilon naught by D into, here it is XB plus K into it is L minus K into LB, it is L, K into LB, okay, minus K into XB, that equal to epsilon naught by D into XB is taken as common factor, K into LB, what is LB? A, plus by XB is taken as common factor, XB into, here it is K minus 1, that is 1 minus K. So, what is the equation for capacitance of the arrangement when the slab is pulled through a small distance x, at that time effective capacitance is epsilon naught by D into Ka plus XB into 1 minus K, XB into 1 minus K. See here once again, XB is taken as common factor, yes, 1 minus K is the equation. So, from this C effective is equal to epsilon naught by D into Ka plus B into 1 minus K into in place of x, B into 1 minus K into in place of x I write. Now, what is x here? It is in place of x Vt I write. What is the distance covered by this one? Distance covered by this one is Vt. So, it is in the form of B into Vt. So, it is in the form of some constant C plus minus BVT into 1 minus K. It is in the form of y equal to minus mx plus c. Y is C effective and it is constant C minus of BVT into 1 minus K. So, we have to plot a graph in between capacitance and time at which it was pulled, that slab is pulled out from capacitor. So, that is both are in the form of the effective capacitance of the capacitor when dielectric slab is slightly pulled out with constant speed V in given time interval, then the effective capacitance in terms of displacement, distance moved by the slab in between the plates of the capacitor is written in terms of speed of the slab and time as y equal to some constant minus mx. So, it is in the form of straight line having negative slope. So, due to that here the nature of the graph plotted between here the variation of capacitance of the system with the time is a straight line having negative slope is the answer. So, that is effective capacitance is epsilon naught A by epsilon naught by D into, what is the formula here? It is it is equal to Ka plus it is xb, b into x is, here it is x is equal to Vt into 1 minus k. So it is in the form of minus mx, y equal to some constant c minus mx in the form. So due to that nature of the graph plotted between capacitance of the system varies in accordance with the time is here a straight line having negative slope. So answer for question number 23 is A. So it is the important and standard model question it is. Okay, right. Next question. Question number 24. A conducting sphere is connected with earth and concentric spherical shell is given a charge q. Choose the correct options. So conducting sphere is connected with earth. That means indirectly the conducting sphere of radius small r is earth end. Now charge is given to outer shell. Now what are the options? Charge on the sphere must be 0. Charge on the sphere must be positive. The magnitude of the charge on the inner sphere is, so this is sphere. Inner one is sphere. Inner one is sphere. Outer one is shell. So already I have written the formula for when charge is given to outer shell, then what is the charge present on innermost sphere or shell is? Charge on innermost shell is equal to minus charge given to outer shell into radius of the innermost shell by radius of the outer shell. Radius of the outer shell. So that equal to minus q into radius of the innermost shell is small r by radius of the outermost shell is capital R if inner shell is earth end. Therefore, charge present on inner sphere is minus q into r by capital R. Here see the options. The magnitude of the charge on inner sphere is q into small r by capital R is the answer for question number 24. Already we discussed the same model question. Okay, right. For question number 24, answer is C. Question number 25. A potentiometer has an uncertainty 0.001 volt. So delta V, the error in the measurement of potential by using potentiometer is 0.0001 volt. If it is used to measure current through a standard resistance, that value R as 0.1 plus or minus 0.1%, that equal to R as 0.1 plus or minus it is 0.01. 0.001 ohm is the error. So 0.1%, the error is 0.1 is the absolute value. In that one error is 0.1% means, sorry, not 0.1%. Yes, 0.1%, the error is 0.1%. So it is not 0.1%, it is 1%. Then 0.1 by 100, that is 0.01 ohm is the error in the measurement of resistance. Okay, now what we want? The voltage across resistance is measured to be 0.2514 volt. What is the percentage of uncertainty in the measurement of current? What is the basic equation for voltage in terms of current and resistance? V equal to IR. So from this I equal to V by R. So what is the error? What is the error in the measurement of current? I equal to V by R, that is delta I by I into 100 is equal to delta V by V plus delta R by R into 100. So delta V is given as 0. What is the value? 0.0001 by V value is, what is V value? 0.2514. 0.2514 plus delta R value 0.01 by resistance value. What is the resistance value? 0.1 absolute value. 0.1 into 100. So from this we can calculate the percentage of error in the measurement of current. What we want, see here, percentage of uncertainty in the measurement of current. After calculation we get 1.04% is the answer for question number 25. So here we know the basic equation for potential difference, current and resistance. V equal to IR. From this percentage of error in the measurement of current is delta V by V plus delta R by R into 100. So, delta V value, delta R value is given. So, from this I calculated percentage of error in the current measured by the potentiometer experiment. For question number 26, 3 point charges Q, 2Q and 8Q are to be placed on 9 centimeter long straight line. So, 3 charges are placed on 9 centimeter long straight line. Find the position where the charges should be placed. Find the position where charges should be placed such that the potential energy of this system is minimum. For having minimum potential energy, larger charges should be separated more distance. So, larger charges be at more distance. Then only potential energy is minimum. So, out of given the data here, what are the charges? Q, 2Q and 8Q. So, larger charges are 2Q and 8Q are separated by a distance 9 meter is given in the data. Okay. So, let small q charge is supposed to be at a distance x from 2Q. Then what is the remaining distance from Q to 8Q? It is 9 minus x. Now, in order to have potential energy minimum, the first derivative of this potential energy function with respect to its position is 0. That is du by dx is equated to 0. So, first we have to calculate potential energy of the system of these 3 particles. So, potential energy of the system of these 3 particles is minus is there 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught for 2Q and 8Q. 2Q into 8Q by here distance is 9 plus 2Q into Q by distance is x plus here it is Q into 8Q by distance is 9 minus x. So, this is the potential energy. So, for minimum du by dx to be equated to 0, du by dx. So, by doing the differentiation of this potential energy function with respect to x, only the variable term is second term and third term, because there is no x term in the first one. So, due to that differentiation of 2 by x plus here it is 8 by 9 minus x. For 2 by x it is minus 2 by x square plus 8 by 9 minus x is 8 by 9 minus x whole square, that is equated to 0. So, 2 by x square is equal to 8 by 9 minus x whole square. By square rooting on both sides, after calculation we get x equal to 3 centimeters. So, at what distance of separation between 2Q and Q, here all these 3 charges potential energy, potential energy will be minimum. If small charge is kept at a distance of 3 centimeter from 2Q and 6 centimeter from 8Q, then only the potential energy of system of all these 3 charges is minimum. Okay. Now, see the options. Here 3 centimeter is the answer. Only one option is there. You substitute x equal to 3 in equation 1. Substitute x equal to 3 in equation 1, then potential energy of the system at that point x equal to 3 centimeter, after calculation you get 0. Okay. Whenever I use the word minimum, almost all it is equated to 0. Okay, according to our syllabus. So, potential energy at a distance 3 centimeter of the charge small q from 2Q and at a distance of 6 centimeter from charge 8Q, the potential energy of the system of all these particles is 0. Okay. So, after calculation we get 0 and 3 centimeters. So, answer is C for question number 26. Okay, right. Next question, 27th question. 20 question. The potential difference between 2 points A and B is 40 volt. If the electric field is uniform, then the value of the electric field at B is, so potential difference between 2 points A and B is 40 volt. If the electric field is uniform, then value of electric field at point B. Okay. See here the options, may be equal to 20 volt per centimeter, may be less than 20 volt per centimeter, both are correct. So, both are correct is the answer. Which one is the correct answer here? Potential difference between 2 points. I considered 2 points A and B separated by a distance, 2 centimeters. The potential difference delta V equal to 40 volt. We know that electric field intensity between these 2 points, electric field intensity E equal to V by D, delta V by 2, delta V by 2 that equal delta V by D that is equal to 2 centimeters. That equal to delta V is 40 by D is 2 into 10 power, here it is 10 power minus 2, that is 20 into 10 square Newton per meter. So, electric field intensity between these 2 points is AB equal to 2000 Newton per meter. If we consider these 2 points are on the line joining of the, these 2 points are on the line of the direction of the electric field intensity. So, that is general assumption by any student, but here these 2 points are need not to be the points on the direction of the electric field intensity. Sometimes here these 2 points may be, on the line of the equipotential surfaces. 2 points are on the lines of the equipotential surfaces A and B. So, here the potential difference between these 2 equipotential surfaces at which the 2 points are on this surface. Let the normal distance between these 2 points is supposed to be, it is delta R, and electric field intensity is E. So, the direction of electric field intensity is always normal to the direction of the equipotential surface. So, these are the equipotential surfaces. The electric field intensity is always imagine normal to the plane of the equipotential surface. Okay. So, this is the direction of ER, but the point here, let it is theta. Then along this direction, the distance between this A and B is supposed to be delta x. What is delta x? Delta x is equal to delta R into cos theta. Delta x is equal to delta R into cos theta. So, here which one is hypotenuse, which one is adjacent side here? So, delta x is equal to delta R into cos, but delta x is more than delta R. So, along this direction, what is electric field intensity? Ex. So, Ex is the electric field intensity along this direction. So, delta x is more than delta R. At the same time, E is more than Ex, that is Ex is less than E. Ex is less than E. So, electric field intensity along this direction is less than E. So, E less than E means what is the potential difference? Then potential difference is less than 40 volt. Between A and B, it may be less than 40 volt. Okay. Along this y direction, if you imagine y direction, along y direction also it may be less than 40 volt. So, what we need here? See the potential at point B may be equal to 20 volts, may be equal to, may be less than 20 volt, may be more than 20 volt or equal to 20. Out of this one may be equal to 20 volt by considering like this, and may be less than 20 volt by considering like this. So, Vx is less than 20 volt. So, between these 2 points it is given as 20 volt. So, 20 volt means here it is what the potential, it is electric field intensity, E is equal to V by D. So potential difference V equal to E into D. So E into D. So on that basis here Vx is also, if it is 20 volt, it is less than 20 volts. So if potential difference is given as 20 volt, then it is less than 20 volt, but it is given 40 volt. So it is also, so distance is also 2 centimeters. For that reason, what we want, electric field is uniform, then the value of electric field at point B. So at that time it may be half of that given value, because so for equipotential surface you have to imagine like that. So if you imagine like this, these 2 points are on the line of electric field intensity, that is on the direction of electric field intensity, it may be potential difference may be 20 volt, potential difference may be 20 volt or 40. At this point it is, when it is 20 volt, difference is 40 volt, here it is 40 volt. So when it is 0 volt, difference is when it is 0 volt, difference is 40 volt, it is 40 volt. So here it may be more than or may be less than or equal to 20 volt by assuming these 2 points are also imagined on the equipotential surfaces separated by a perpendicular distance delta r, at which the potential difference between these 2 equipotential surfaces is given as delta V. So simply on that sense we have to tick the answer for this question. So maybe less than 20 volt per centimeter, maybe equal to 20 volt per centimeter by assuming like this. Okay, so for this question answer is both A and B are correct. So answer is A and B are correct. So answer is C for this question. Next question, is there any angle is given here, theta is not given. So theta is not given, you have to assume for any angle, any value, theta may be for any value in between 0 to 90, other than 0 and other than 90, then for that it may be 20 volt per centimeter. For 0 to 90 it may be equal to 20 volt per centimeter. So but absolute maximum value is 40 volt per centimeter, 40 volt, here it is the potential difference, but electric field we want. So electric field is, here it is E equal to V by D, that is 20 volt per meter. In centimeters it is given, so 2 into 10 to the power minus 1, 2000 it is, but in centimeter we want 20 per centimeter. 20 per centimeter is the electric field, 2000 volt per meter or 20 volt per centimeter. In this way it is potential difference is 40 volt, here less than 40 volt. So electric field intensity E equal to E less than V by D, that is less than 20 volt per centimeter. So for question number 27 answer is C. Next question number 28. The 2 equal point charges are fixed at x equal to minus a and at x equal to plus a on x axis. Another point charge capital Q is placed at origin. The change in electrostatic potential energy of the system when Q is slightly displaced to small displacement x along the axis. So when this Q is Q and small q, the 2 equal point charges, 2 equal means Q and Q are separated by a distance 2a, and another charge capital Q is placed at origin. When it is slightly displaced means initially before displacement the system of these 3 charges are in equilibrium. Now when the system of these charges are in equilibrium, when it is displaced slightly, then only it executes some oscillations. But here what we want, only we need here the change in electrostatic potential energy. What is the initial potential energy of the system? So 2 charges are separated by a distance a, 2a. So it is 1 by 4 pi epsilon naught q into q by distance is 2a between the end charges plus q into capital Q by a plus q into right hand charge is q by a. It is the distance potential energy of this system of these three charges initially. So after displacement, what is the final potential energy? 1 by 4 pi epsilon naught minus is there into q by 2a is same plus, but here this small capital Q is displaced to small distance x. Therefore, q into capital Q by, in place of a I write a plus x plus for last two charges it is q into q by a minus x. So change of this one, change of this potential energy equal, this becomes 0. Only this is the change. So therefore it is q into 1 by a minus 1 by a plus x, final minus initial, 1 by a minus 1 by a plus x and plus of q into 1 by a minus x minus 1 by a. So after calculation you get q by a plus x minus a plus x minus a, x by a into a plus x plus q into a minus a plus x, a minus a plus x, it is x by a into a minus x, that equal to q x is taken as common factor 1 by a into a plus x plus 1 by a into a minus x. So after calculation, the change in potential energy, here you get, see here, a minus x plus a plus x, one minus is there. So a minus x minus of a minus x, it is minus plus x, 2x is there, 2x into x square. So the change in potential energy is directly proportional to x square. You do the calculation here. This is the equation for initial potential energy of the system of these two charges. This is the final potential of the system of these three charges. Then by taking the difference of these two, we get the equation, and only we want relation between change in potential energy and the displacement of the charge q from mean position. So from this here minus is there in the calculation. So we get minus x is there, minus 2x into x square. So change in potential energy is directly proportional to x square after calculation. So answer is B. For question number 28, change in potential energy is directly proportional to x square is the answer for question number 28. Question number 29, last question of this live discussion. The electric potential in a certain region of the space is given as V equal to 3x square plus 4x in a certain region. In this region, the equipotential surfaces are, suppose when you know potential equation, how you calculate electric field intensity in that region, E equal to minus of dou V by dou x only into I cap, because only it varies along x direction. So due to that we get only Ex bar. So therefore Ex bar is equal to minus of dou V, it is 6x plus 4 into I cap, that equal to minus of 6x plus 4 into I cap, it is, so electric field intensity in that region is along negative x direction, So compulsory equipotential surface must be perpendicular to negative x direction. So compulsory it must be YOZ plane. Compulsory equipotential surface must be YOZ plane. So equipotential surface is perpendicular to electric field vector. So therefore it lies in YOZ plane. So indirectly parallel to YOZ plane or in YOZ plane. So equipotential surface are imagined parallel to YOZ plane. So this is equipotential surface, this is the direction of electric field intensity. This is under equipotential, this is under equipotential surface. So equipotential surface are parallel to YOZ plane if electric field intensity is towards negative x axis. So for this one, your answer is parallel to YOZ plane is the answer for question number 29. So, okay, right, for question number 29 answer is B. So, in this live discussion, I explained 29 questions regarding the topic electrostatics and current electricity. Please subscribe for this live discussions for future classes. Okay, thank you all.